introduce. So, very good morning, or a very good afternoon, or a very good evening, wherever you are, and you are following this very interesting seminar. Today we have Professor Tetsuo Hatsuda as a speaker, an expert on lattice QCD and nuclear physics and hadron physics. Professor Hatsuda obtained his PhD in the Kyoto University. And then actually spent around 6 years on different positions in the US. So in Stony Brook, then at CERN, then again in Washington, where he was the research assistant and also assistant professor. And finally, in the middle of the 90s, he decided to go back to Japan. And first, he went to Tsukuba. Then he was associate professor in 98 at the Kyoto University. And then he changed to the Tokyo University in 2000. And since then, he's professor. Actually, since 2019, he's emeritus professor at the University of Tokyo. On the other hand, parallel to his appointment in the Tokyo University, he occupies also an important position at the RIKEN Nishina Center. Indeed, he is their chief scientist since 2012. And actually, since 2016, he became the program director of the RIKEN iTHEMS. We all know him in the field as the leader of the HAL QCD collaboration. I mean, the HAL QCD collaborations is in the forefront of the calculation for hadron physics and nuclear physics on the lattice. And this is also what today Tetsuo will talk about, since the title of his talk is Hadron Interaction from Lattice QCD. And I'm sure that he will show us how theory meets experiment. It's a pleasure to listen to your talk, Tetsuo.
Okay, thank you very much for the nice introduction. So I'm now in Berkeley, so my time is 6 o'clock, but good morning and good afternoon. So today, I'm going to talk about this hadronic interaction from Lattice QCD. And then first I'll give you some introduction, for general introduction, and then go to the discussion on how you calculate the hadronic interactions from Lattice QCD, and we use the method so-called HAL QCD method. And then I go to the comparison of the recent Lattice QCD calculation and the experiments at RHIC and LHC and J-PARC. That is very, it's a very fantastic collaboration and also interaction between the theory and experiment going on right now, and then summarize. Okay. So here is a general introduction. What we would like to do is to starting from QCD Lagrangian, which is composed of gluonic part and then the quark part and the quark-gluon interaction. And then it's just a very simple one-line equation, but of course, dynamics is very complicated. So only way which at the moment, which we can do to calculate in a non-perturbative way the QCD result is the Lattice QCD simulation. So far, people have done some calculation related to the QCD vacuum, and then the single baryon or single meson properties. But of course, eventually we would like to go further to study the interactions and then interaction of the meson and baryons, and then go to the nucleus and the eventually neutron stars. And so this is a long way to go. And Lattice QCD, what we are going to do is to make a bridge between single baryon analysis to the 2 baryon or 3 baryon analysis based on the first principles. And of course, this can be tested, or we can confirm the experimental result going on at RHIC or LHC or J-PARC, where people can study the 2 particle correlations from the interaction of the hadrons or the hypernuclear spectroscopy. So that I'm going to talk in the last part of my seminar. Okay, so my talk is based on our Lattice QCD studies, and then later I'm going to discuss the relation or comparison with experimental data. Okay, so this is a overview. And then this is really a basic introduction, but QCD is really non-perturbative in the sense that the running coupling constant, alpha s, which is g squared. This g is a coupling constant of QCD, g squared over 4 pi, changes as a function of the typical energy scale involved in the system. For example, in the PP, high energy PP bar, or electron positron annihilation, and so on and so forth, the energy scale is large. If the energy scale is large, then the coupling constant decreases, like this data, but at low energies, it increases. And then eventually, you cannot anymore use the perturbation theory. Therefore, the energy below 1 GeV is rather non-perturbative. That's why we need to use some non-perturbative technique like lattice QCD. The nice thing is that as you can see from here, the coupling constant is well determined, this G as a function of the momentum or energy. Also, the quark masses, which is an input parameter in QCD, can be also determined very well, actually from lattice QCD simulations of the single hadrons like proton, neutron, pion, and so on and so forth, by comparing the hadronic masses, experimental hadronic masses, and then QCD simulations. You can determine the masses of the light quarks like U quark mass, D quark mass, S quark mass. And most of the time, I'm going to talk about only UDS in my seminar, but so-called MS bar mass at 2 GeV scale, UD is something like 2 MeV, 4 MeV, with some relatively small error bars in these days. And then strange quark mass is 100 MeV, or 92 MeV plus minus 1.1 MeV. So now we know essentially the behavior and the strengths of the coupling and also the quark masses. Therefore, it should be able to, for example, reproduce the nucleon mass, for example, starting from these light quarks in a non-perturbative way. That is the lattice QCD simulations. So I'm not going into the details of how the calculation is made on the lattice in detail, but I mean, essentially you have a discrete space-time, I mean, discretized space-time, and then in these days, the box size is something like, in our simulation, for example, the box size is something like 10 Fermi. And the lattice spacing, of course, eventually you have to make this lattice spacing 0 by having some extrapolation. But typical lattice spacing we have now is 0.08 Fermi, less than 0.1 Fermi. And then in the case of the single hadron, like baryon or meson, what you do is to calculate the temporal correlation of these particles. And so this is written as RT. I mean, in the Minkowski space-time, if you have a mass at rest, then the temporal correlation is just oscillating, I mean, in time, right? Exponential IMT, this is the mass of the particle at rest. But if you go to the Euclidean time, then IT minus IT, IT becomes tau, the Euclidean time, therefore it's exponential damping. So it's, I mean, conceptually, it is relatively easy to extract the mass of the particle by looking at this temporal correlation function, and then just taking a log of this R to extract the slope. That gives you this M. Of course, there are lots of, I mean, sophisticated techniques to extract this M, but essentially what is going on is something like this. And then here is already 10 years ago, people have calculated the masses of mesons and the baryons. Here, the bars are experimental data. And for example, the delta baryon has a width. So this is a physical width of the delta. And then, as I said, we have a few parameters in lattice QCD, like U quark mass, D quark mass, and then strange quark mass, and then coupling constant. So there are 4 parameters. In this simulation, they assume UD quark mass are degenerate. So now you have 3 parameters, which can be determined by pion input, kaon input, and then the cascade input. Cascade is a SSU or SSD baryon. And then the rest is a prediction from lattice QCD. And as you can see, they are quite consistent within the error bars, statistical and systematic error bars with the experimental data. So this is a status already 10 years ago. And now people have started to calculate the proton-neutron mass difference, taking into account the QED effect. And then you can essentially reproduce 1.3 MeV mass difference between protons and neutrons and so forth. So it becomes quite accurate, at least for single hadrons. One more example. This is already 4 years ago by Jason Chan and the people in Lawrence Berkeley lab. Jason is also a member of iTHEMS, was a member of iTHEMS. And they have calculated not only the mass, but also the axial charge of the nucleon. And that is important because, as you know, this neutron beta decay is controlled by this GA. And then what they found is the number with this accuracy. I mean, GA has been long studied, and then it was relatively difficult to come to the number close to the experimental numbers. But now, experimental data is here with this error bar, like 1.272 plus minus 0.002, and then already 4 years ago, GA is this accuracy. Therefore, now you can determine the lifetime of the neutron in a rather accurate way. And then, as you may know, there are two experiments, different experiments, which have a different number for the neutron lifetime. Therefore, eventually, whether it is sort of the experimental problem or if there's some light, exotic particle, which is involved in the decay of the neutron, then that may be also an interesting possibility. That kind of thing can be tested by doing this lattice QCD calculation. Okay, but today's topic is not just a single baryon, but we would like to extend this fantastic single baryon calculation into the two baryon, and then it's not that trivial. So I will show you a little bit about the formalism, not too much, because I want to go to the comparison with the experimental data. But let me show you by using few slides about how to calculate the baryonic interactions. So, of course, I mean, the reason why we do this baryonic interaction calculation is that it may be related to the exotic hadrons, like a dibaryon or tetraquark, and those kind of interesting possibility of the new bound states. Also, if you know this baryon interaction, hypernuclear interaction, for example, then you can use it to study the spectrum of hypernuclei, which I'm going to show a little bit later. And eventually, I mean, of course, you cannot go too further in dense matter, but at least relatively low density region, you can study the behavior of hyperons inside neutron matter to see what is the effect of that kind of interaction on the equation of state of hyperonic matter. So there are lots of interesting physics behind the interaction between two baryons. Okay, so let me go to a little bit about the basics of the hadronic interaction calculation on the lattice by few slides. So actually, the interaction of, so we are talking about hadronic interaction, and that is the interaction between composite particles, right? I mean, it's not an interaction between elementary particles. There's a composite particle and then they interact. That kind of thing has been first, as far as I know, studied intensively by HAL and Nishijima-Zimmerman. Originally, they worked together, but eventually they wrote paper independently. But what they have had in mind, at that time, it's 57, so there's no QCD. So they were talking, they have in mind about, say, proton-deuteron interaction, that kind of, or deuteron-deuteron interaction, that kind of thing. How to treat the interaction between composite particles in the framework of the quantum field theory. And that has been also generalized by Boschers. And the essential, points which they found is that you can generalize the usual Riemann-Zimmermann reduction formula for elementary particles to the reduction formula for composite particles. And then this is one first point. And second point is that it is enough to consider only the local composite operators to derive the, say, the phase shift or binding energy of the two composite particles. This is a theorem called the Bosch's theorem. And then much later after QCD, Lucia was the first who developed the interaction of the composite particle and the phase shift and so forth in terms of the QCD. And then we have proposed a new method, which contains as a part the Lucia's method, but it's a sort of the generalization of the Lucia's method. And then there's some review article, but yeah, you can say take a look at the recent progress theoretically and experimentally. I mean, lattice result in this review. The basic idea, as I said, what you would like to see is what you want to study is a correlation of the two composite objects like X and Y. This is the spatial point, and this is the imaginary time. It is on the lattice. So you first create 6 cones. And you can have various or infinite many ways to create 6 cones. That's fine. You can take one and then you can change it. But, and then that gives you a useful information. But suppose you create some 6 cones at certain time, say time 0, and then let them propagate. If you wait long enough, then each, say, nucleon becomes a ground state, and then still they interact as elastic scattering. Okay, so if you wait until, say, above 1 Fermi or so, then the nucleon or baryons, the ground state baryons, interact with each other. Of course, at long distance, I mean, you can define single particles and single hadrons, but if they interact, I mean, there are lots of different states coupled to this. But essentially, what you study is the beta-salpeter amplitude, or we call it number beta-salpeter amplitude because number is the first who discussed this kind of thing. But this F is essentially the beta-salpeter amplitude as a function of the relative distance R, and then the time T. Okay, and J means the information on how to create these 6 cones. Depending on this source, you can have a different weight factor for different scattering state. So psi n, we are in the finite box, therefore psi n is a discrete wave function, so to say. And then the En corresponds to the scattering energy, including the rest mass of the particles. And then this Aj is a coefficient which depends on this J, the weight factor. That also gives you a good information for the interaction of the particles. And then you can derive, in general, I mean, without approximation, you can derive a sort of the beta-salpeter type equation, which is satisfied sort of the Klein-Gordon type equation with the derivative with respect to the relative distance, and then the relative, I mean, the time, and then the mass square is this m is the mass of the asymptotic state. So in the case of the nucleon mass. And from here, I mean, you can, in general, derive this kind of formula, but U is unknown, and U actually can be determined. This is a sort of the potential between the particles, interaction of the two hadronic particles. Since we measure the FJRT on the lattice, and then you can do numerical derivative of this side. Therefore, in principle, you can invert this equation to derive this U. So it's more like inversion of the Lippmann-Schwinger equation. You have a Lippmann-Schwinger equation, you have a T matrix written in terms of the potential. Now on the lattice, it's like an experiment. You know the T matrix on the lattice, and then you derive the potential instead of assuming the potential. That is the basic idea, and that you can justify it from quantum field theory. So important point is that it's a derivable from, in general, quantum field theory, and fully relativistic, as you can see from this kind of Klein-Gordon form. And then in the non-relativistic approximation, you can derive a Schrödinger type equation. And then you can show that the asymptotic behavior of this F for large R gives you the correct S matrix. And then U is rather localized in space, so that it's rather insensitive. I mean, F is very sensitive to the lattice volume, but U is localized and rather insensitive to the lattice volume, meaning that once you obtain U, then you can calculate the observables in the infinite volume by using this U to get some binding energy or scattering phase shift, and so on and so forth. Also, by using the information of this different J, usually, I mean, this U is non-local, but you can, at low energies, you can decompose it to the central tensor spin orbit, just like a usual nuclear force. One can be, in principle, determined by changing by using different J or combination of the J, because by changing the J, you can change the coefficient, the weight factor, so that you can decompose. By using that information, you can in principle decompose leading order, next leading order, and so on and so forth. But today's talk, I focus only on the central part of the potential, which is the most simple one at low energies. So this is the second slide for the formalism. So this is a procedure that you derive the phase shift or binding energy from lattice QCD in this HAL QCD method, which was in a very, in a clear presentation of this kind is given by this paper, the last one by Yan Liu, our collaborator in HAL QCD, published very recently. Of course, we have been doing this for a long time, more than 10 years, but yeah. So suppose you take omega omega, it's the simplest baryon, SSS interaction. So you calculate this F on the lattice, and then by using this Bethe-Salpeter type equation, you derive this central potential at low energies, right? So it looks like this one. This is a calculation of omega omega at pion mass 146 MeV. So it's very close to the physical point, not exactly, but close to the physical point. And this is a projection of the central potential into the z=0 plane, xy plane. So what you see is that the interaction range of the potential. So this is the attraction pocket here, and then repulsive core there. And then you have something like a 1 Fermi, 2 Fermi size. So it's much smaller than the lattice spacing, right? In our case, 8 Fermi. Sorry, lattice box size. So it's rather insensitive to the lattice size. So you get this kind of potential. And then once you get it, and then you can just use it to calculate the phase shift in the infinite volume. Then it turns out that you have one very shallow bound state for omega omega, and phase shift start from 180 degrees, and then you have attraction. But on the other hand, you can use this potential to calculate energy eigenvalues in a finite box. And then, and also the wave function, like Bethe-Salpeter wave function. And then what you find is that this is a ground state, this is first excited state, second, third, and so on and so forth. So as you can see, this is a periodic boundary condition. And then the two baryons are confined inside the box with periodic boundary conditions. Therefore, the wave function is really distorted at the boundary. Okay, but all these wave functions gives you essentially the same potential, because it's so this single potential dictates all these wave functions, and then you can find some energy eigenvalues or the amplitude in a finite volume. This EN is what obtained in the Lucius method by other direction, but you can compare the Lucius calculation of EN in principle with this HAL QCD, and then in certain cases they agree at least up to certain levels, and at least we are talking about low energies. So most of the time we are talking about, say, E0 or E1 or those kinds of things. So this is the connection between HAL and Lucius. So Lucius calculates this EN directly. It's hard, especially for the baryon-baryon interaction. So if you do it in a wrong way, then you get something wrong result. But if you need to do it very carefully. But if you do it, then in recent years there's some consistency already found between HAL QCD potential calculation and then EN here from Lucius. So rest of my talk, I think I'm going to use this kind of potential because it's useful. Of course, the potential itself is not the observable. If you change, say, J, for example, the potential, okay, sorry. If you change J, and then also if you change the, say, the operator which you use in X and Y, in principle, the potential may change, but the observables is, it does not depend on such kind of choice. It's just like choice of the, I mean, it's not exactly the same, but it's the choice of the renormalization point in QCD. And then, although you can choose any renormalization point, physical observables, cross-section, and so on and so forth, should not depend on the renormalization point. It's similar, of course, conceptually similar, not exactly. Okay. So, from now on, I'm going to show you some result of lattice QCD calculation. And then in some cases, you can compare with experiment. Sometimes experiment is first, and then lattice QCD come later, or the vice versa. So that is an interesting interplay between lattice QCD and the experiment. So we have a so-called HAL QCD collaboration, hadrons to atomic nuclei lattice QCD collaboration, and then members are here. We have something like, I don't know, more than 10 members. Recently, from Beijing, Yan Liu and Hui Ton joined our collaboration. And then for past 10 years, we have been using K computer, which was at certain point in 2011, it was the world's fastest computer, 11 petaflops. And we have been generating the gauge configurations with 8 Fermi cube, pion mass 146 MeV, a little heavier than the physical pion mass. And now we are generating configurations on Fugaku, 40 times faster computer after this K computer in RIKEN. And again, the same volume, but the pion mass is now the average of the pi 0 and pi charged. So it's 138 MeV. So we still assume UD Cork masses are the same, isospin symmetric case, but other than that, it's a physical point simulation. But of course, today, we don't have, I mean, we are still generating the configuration and analyzing some data. So we are going to show you some of our result from the K computer. So this is an interesting figure which made by Doi-san. Lattice QCD is rather, I mean, the error bars are relatively small for heavy Cork masses. Therefore, for example, this one, omega-omega interaction, has a relatively high, I mean, small error bars compared to, say, nucleon-nucleon or lambda-lambda. Because if the Cork mass is heavy, then the fluctuation becomes suppressed. On the other hand, experimental data, of course, it's easier to do nucleon-nucleon, and then difficult to do, say, omega-omega. Not impossible, I think, but then we can compare the result, between lattice QCD and then the experimental data, probably in between. So this is what is going on now. So I'm going to first show you lambda-lambda and n cascade interaction, and then go to the n omega, and then omega-omega in this order. Okay, so it's about the time. 30 minutes passed, so I think it's good schedule now. Okay, so what kind of interaction we are going to consider? We are going to study the interaction between among octet baryons, or interaction between octet and decouplet. But most of the decouplet particles are unstable with respect to the decay into the octet hadrons through the strong interaction. Only omega has a small width. If you switch off the weak interaction, then these particles with this green circle are stable against strong decays, and only omega is stable against strong decay in the decouplet variant. Therefore, I think not only this interaction among octet, also the interaction between omega and decoupled octet particles would be a very interesting topic, both experimentally and then I think theoretically too. So what is the SU3 classification? Of course, SU3 flavor symmetry is broken, but still it's a good starting point to discuss or classify as a system. So suppose we have an octet-octet baryonic interaction. So it's octet-octet that decompose into, if you assume SU3 symmetry, into different flavor multiplet. And then nucleon-nucleon spin singlet interaction channel is in 27 multiplet, and then deuteron channel is in 10 star multiplet. And then interesting H dibaryon, which is a spin singlet, S wave, total spin 0. This kind of in spectroscopic notation, this is H dibaryon, which was originally discussed by Jaffe in the Berg model. It's in singlet, in the SU3 classification. But of course, SU3 is broken by the mass difference between the strange quark and the UD quark. Therefore, eventually, these representation mix with each other. And that is very important. So that I'm going to show you by taking this H as an example. So suppose we have a same mass for UD quark and strange quark. And suppose we have say about 100 MeV for UD and S. So 100 MeV is something similar to the physical strange quark mass, but much heavier than the physical UD quark mass. But suppose we have this kind of situation. Okay. And then since SU3 flavor symmetry is not broken, it's exact. Therefore, N cascade, sigma sigma, lambda lambda, all the octet baryons have the same mass. Therefore, all the thresholds are the same place. So this bar is a threshold. And then if you calculate this singlet hadron interaction, then what you find is that in the singlet combination of the, let's say, H dibaryon channel, what you find is that you have a attraction and then attractive core. So it's whole attraction. There's no, unlike the nucleon case, it's a whole attraction. This is a potential as a function of the distance. So attraction is below, say, 1 or 1.5 MeV, 5 Fermi or so. And then you can calculate. I mean, this is, again, I would say, not a physical observable. Therefore, you have to calculate the phase shift or binding energy and so on and so forth. And then what you find is that there is a very shallow bound state, like 20, 30 MeV binding energy. That number itself, still, it's not conclusive yet, but you would have a bound state. And then, so very shallow bound state below lambda lambda threshold. This is nothing but the H dibaryon. So it seems the H dibaryon exists in this hypothetical world. But of course, our world is not SU3 symmetric. And then, as I said, say lambda lambda, sigma sigma, and cascade, these states mix with, I mean, it's a mixture of the singlet or octet or 27 plet with the Krebs-Kollmann coefficient. So for example, lambda lambda, the main contribution by looking at this one is coming from 27. On the other hand, N cascade, the main contribution is coming from the last column. It's a singlet. So probably the remnant of this attraction is coming from, encoded in this N cascade interaction. And that is actually the case. But on the other hand, there is an attractive core in singlet, but octet and 27, there is always a repulsive core, which you can show again on the lattice. Therefore, since they mix with each other, therefore, eventually what you find is that the N cascade interaction is rather attractive because of this. So there is some remnant of this attraction, but because of the mixture of the other states, you have still a remnant of the repulsive core. And then the lambda lambda sigma sigma, the main contribution is other channels. And then what you find is that they say red one is lambda lambda. So you have some attractive pocket, but you have also a repulsion at short distance. And then there's some coupling. This is a lambda lambda and sigma coupling, which is relatively short range. And then also because UD quark mass is much smaller than strange quark mass in the physical world, then the threshold here split into 3. sigma sigma and cascade lambda lambda. And then it turns out that because of this and cascade relatively weak attraction with relatively strong, short, weak repulsion, you may find some resonance or virtual state and so on and so forth, which we don't, we are not sure yet under the resolution of the Lattice QCD data yet, but there may be something in this region of this remnant of this H diversion, but not below lambda lambda. That is what we found. Okay, so it is highly likely that there will be no H diversion below lambda lambda. It may be something near and cascade threshold due to the SS3 symmetry breaking. So in that sense, SS3 symmetry is very important. And then in terms of the potential, this is lambda lambda interaction, the weak attraction, and then N cascade, relatively strong attraction, but weak repulsion. And then there are some coupling. But these couplings at low energies, since this is short range, therefore it is rather suppressed, at least at short distances. I mean, low energies. This has been shown 2 years ago by our colleague, Sasaki, and the HAL QCD collaboration. So let's come to the experiment. So the one thing which you can check in principle of this N cascade or lambda lambda interaction is a femtoscopy. And of course, there are long history, RHIC and LHC in PP, PA, and AA. And then you create some fireball, I would say, and then you produce, say, N and cascade, and then they have a final state interaction with K star is a relative momentum in the center of mass frame. Then this experimentally, you can define some correlation function. There's number of pairs from the same event and the mixed event ratio with some correction factor. Theoretically, is convolution of the source function here, how the source is distributed times the wave function square of this two-particle system. Therefore, you need some wave function which you can calculate from Lattice QCD potential. So this kind of formalism has been, developed since 1977. So what is very important is that depending on the first of all, the behavior of this correlation function depends on the, of course, the interaction strength. But let's take attractive case only. Then, if there's no bound state, this correlation function as a function of the relative momentum, since it is attractive, and then I'm going to talk about the different particles. No statistical effect, Pauli principle. In that case, because of the attraction, you have this kind of behavior. So you have C, the correlation function is above 1. And then if you have a bound state, for example, then you may have some dip and then attraction. Or if the source size is very large, then the effect, if you have a bound state, the scattering wave should be orthogonal to the localized bound state wave function. Therefore, it should have a node or suppressed at short distances. And then because of that kind of effect, for large source size, it looks like a repulsive interaction if you have a bound state and then the source size is large. On the other hand, if you have a bound state but source size is relatively small, then still you can see an effect of the attraction or the enhancement wave function outside of the source. Rather outside of the interaction region, and then you have an enhancement at low energies. So you have a big change as a function of the source size in the case of if you have a bound state, while you have of course, there's some change, but not that qualitative change in the case that there is no bound state. So by looking at the scattering of the two particles, and by changing the source size can be changed by comparing PP and then PA and PP and AA, for example, or even with AA, for example, central origin and then the peripheral origin, you can also change the source size. So by using this by combining these kind of ideas, or then you may be able to tell whether there is a bound state or not, even by the scattering data. So this is a basic idea. This collaboration has published this one. I mean, in say lambda correlation in PP and PA, and then excluded the scattering lengths and the region of some scattering lengths and the effective range. And then many of these points are calculation of the various potentials, and HAL QCD has, I mean, other potentials you can change, you can dial the parameters so that you can move around in this space. But HAL QCD, there's no adjustable parameters, not much actually. In error bars, we have this prediction in some way. And then so far it is consistent. As I said, there's no, I mean, in Lattice QCD, probably we will not have any bound state. Therefore, we are in the region in this negative scattering lengths in the usual, I think, which, yeah. So no bound state correspond to the negative of the scattering lengths. That is our convention. So at least, I mean, lattice and then femtoscopic data for lambda is consistent. And then after that, there is another paper in N cascade correlation in PP collisions. Now, again, this is a relative momentum, and this is a CK, the correlation function. And if you have only a Coulomb attraction, since it is proton and then cascade minus, still you have attraction, but there is an extra attraction coming from probably from the strong interaction. And then these are the data. And then if you use the HAL QCD potential in this P omega, this proton omega minus channel, like this one. By fitting this one, you can calculate the wave function. And then what you find is that there is a consistency between lattice data and then experimental data in a rather quantitative way. So that's amazing. And then what is missing here is that the, in this curve is a coupled channel effect, because P cascade and then lambda, they couple in principle with each other. Therefore, in principle, you need to take into account that kind of coupled channel effect. And that has been done by Kamiya and then other people. And then this is N cascade and then lambda coupled channel calculation. And then you see effect. I mean, as I said, effect of the coupled channel is not that strong. So the final result is almost similar as the previous one. And then, but we can talk about the lambda and P cascade simultaneously. Lambda, although it's attractive, but of course, since they're the same particle, therefore, generally there is a tendency that the C is suppressed. And then only with the quantum statistic effect, you have, okay, so there is a relatively, so this dashed one is the quantum statistics with the source size 1 Fermi in the PP. This is for the PP case, yes. But there's some attraction, therefore you have some enhancement over this dashed line, but not too strong attraction. Okay, so what about the comparison between PA and AA? I mean, in the case of the PA and AA, as I said, probably from Lattice QCD tells us that probably we don't have P proton cascade minus bound state. So probably we are in the region here. So this is the case without bound state, attraction but no bound state, and here the attraction with bound state, right? And then there is a data from this P nucleus, and then again there's a comparison with Lattice QCD. So it should be possible to compare this result with PP case and see how this curve consistent with this kind of a tendency. That I don't know yet. It's only about comparison of the data that I haven't seen the direct comparison. But yeah, so this is interesting. I mean, should be an interesting comparison. And then, as I said, the STAR have done a gold collision with, this is a central collision and this is peripheral. again, by doing this one, you can compare, you can change the source size. And then from here, you can directly see that the peripheral is higher. So this curve is for the small source size, and this dashed one is for the large source size. So if you compare this, at least the tendency of the data is consistent with this kind of behavior. That means that it could be no bound state also in cascades consistent with the lattice QCD prediction. But this kind of thing should be, examined in more detail using coupled channel calculation and so on and so forth. So maybe no bound state. In some model like Nijmegen model for the hyperon interaction, in some model they have some bound state, but in HAL QCD or Lattice QCD does not support that kind of idea. Also, since although there's no bound state, still cascade and nucleon has some attractive interaction. Therefore, you may have some cascade hypernucleus that has been discovered, and there are many discovered already so far. So in this J-PARC experiment, you have a cascade into this nuclear, and then you have some bound nuclear formed, and then decay into two hypernuclei. And then from this data, they concluded that there is attraction because you have a bound state, and then also because of the lifetime, the coupling between N cascade and lambda would be small because you can see this binding. That is at least qualitatively consistent with what HAL QCD predict. So far, there are many cascade hypernuclei found, and then still you need to make a detailed hypernuclear level calculation, but probably this is related to the 1s state, and then this could be 1p state. So they may have already found not only 1s but also 1p various emergent data. Okay, so this is a nucleus like relatively medium heavy nucleus, cascade hypernucleus. But what would be the lightest cascade hypernuclei? Is it so? Probably we don't have proton cascade minus bound state, but what will be the lightest one? And that we have studied. The Emiko Hiyama is the one person who did this kind of few body calculation by using our lattice QCD data potential. And then possible candidate would be either helium-3 or triton cascade. The binding energy is very small, maybe less than 1 MeV, but still, this is the first, cascade, lightest high cascade hypernuclei. So it will be interesting to find this kind of cascade hypernuclei, or at least the interaction between the triton cascade or helium-3 cascade using femtoscopy. If you can do that, that would be very interesting, I think. Also, can we test the spin isospin dependence of the cascade nucleon interaction? At least up to now, the femtoscopy, you cannot differentiate the spin dependence of the cascade nucleon interaction. But can you do that in the case by using hypernuclei? And that has been discussed very recently, again with Hiyama-san. And then in this case, if we have this 2 alpha with neutron and cascade, then it turns out that the neutron and cascade have a very shallow binding to the 2 alpha. And since alpha is a spin isospin saturated nuclei, therefore you can test the interaction, spin dependence of this cascade neutron interaction or cascade nucleon interaction by the energy levels of this hypernuclei, which is not known yet, but you may be able to create by using kaon beam in J-PARC. But I'm not going into the details of this kind, but there are some studies, cascade nuclear interaction in hypernuclei too. Okay, so by using 10 minutes, I'm going to discuss a little bit more about N omega, which was first discussed, I think, as far as knowing, Koch model by Goldman, and then and also Oka. They claim that the spin 2 channel, total angular momentum 2 spin 2 S wave in omega would have a bound state using Cork model at that time. And also the omega, this was predicted in terms of the SCAR model, but omega, interaction between two omega with spin singlet may have a bound state. That kind of thing has been discussed before using the phenomenological models. So what Lattice QCD tells us about this kind of thing in a quantitative way. And then we have done in 2 years ago and also the last year. This is the case for the N omega spin 2 potential. So this is a spin 2. So essentially, I mean, this is a parallel spin, nucleon and omega. There is no Pauli principle, Pauli effect in the Cork level because omega is SSS and N is UUD or UDD. Therefore, they can just overlap with each other. So there is no Pauli effect. But that does not necessarily mean that the interaction is attraction at short distance or repulsion at short distance. That depends on the gluonic dynamics. And it turns out that in this N omega case, you have a whole attraction, just like the H dibaryon case. It's a whole attraction. On the other hand, omega spin singlet, just look at only this red one, omega spin singlet. So it's omega. Again, there is no Pauli repulsion here because omega is SSS, but it has color degrees of freedom. Therefore, if as far as you have spin up and down, then they can overlap with each other. There's no Pauli effect in this channel, but still you have some repulsion at short distance. Again, due to the gluonic interaction. And actually, on the long time ago, in the Cork model, by using one gluon exchange effect, they have already knew, some people knew that there is a repulsion in omega and there is attraction in N omega only by using one gluon exchange. So somehow we are reproducing that kind of qualitative idea in terms of the lattice QCD. So so there is a whole attraction and then some weak repulsion and then some attraction omega. And then by calculating the phase shift, in both cases, we have a shallow bound state. Phase shift starts from 180 degrees in both cases. So the function of the typical distance between two baryons and then binding energy. This is neutron, which we know, the 2.2 MeV binding energy with the typical distance, very large. And then the P omega minus in spin 2 channel is here. We include Coulomb interaction, therefore we have some extra attraction due to Coulomb, while omega, although you have attraction, but there is a Coulomb repulsion. Therefore, without Coulomb, it's about the same place, something around 2 MeV, but then it split into this way or this way with errors. So you may have some quasi-bound state of N omega. When I say quasi, because it can, in principle, decay into the two hyperons like lambda sig, in this case, lambda sigma, for example. And omega, if it is a bound state, it is a bound state because there's no channel below. So theoretically, this is much cleaner. This is sort of a little bit ambiguous. There's some ambiguity because we haven't taken into account that kind of a coupled channel below N omega in our calculation, although the effect cannot be seen, at least within our accuracy. So again, Alice collaboration, they have measured N omega correlation, and then this is, green one is Coulomb, and then either this or this is from Lattice QCD, and then why there is some ambiguity, because we can calculate only the spin 2. If we spin 1, then there is a fall apart decay into the octet baryon. Therefore, in our Lattice QCD calculation, we cannot really see a stable signal for the baryonic potential. Therefore, we don't have any information of the spin 1 channel unless we do the coupled channel calculation in the future. Okay, so there's some ambiguity, but there's some extra attraction probably over this Coulomb. Okay, in N omega in PP. So in this case, you may have some bound state. So we are in this region probably. And then this is a star collaboration. This is I think gold, and then left panel is central, and then the right panel is peripheral. So essentially, as before, you may be able to compare the central and peripheral ratio. I mean, a comparison between central and peripheral. So this is larger, smaller source size, so corresponding to this one, and this is a larger source size, should correspond to this one. But this figure does not contain the Coulomb interaction. Well, I mean, there's a Coulomb attraction in omega. So in both cases, you have some Coulomb attraction. Therefore, it would be better to cancel that Coulomb interaction by taking the ratio, which was proposed by Morita and the people. So if you take the ratio of this one first divided by, sorry, the other way around, this one divided by this one, then you see a large dip here. The scale is 0 here and 1. So if I believe in this data, the central point itself, then you have a large reduction as you go to the peripheral. So this is if you take this ratio, therefore this is peripheral and this is central, and then am I saying correctly? This is smaller than 1, and if you take the ratio between this divided by this divided by this one, this is a large one. Okay, so it's sort of the opposite direction, but yeah, so I don't know. I'm not sure whether we can really, I mean, compare directly this figure and this figure, because the figure here, the x-axis is the momentum times r. R is involved here, so I cannot really, I mean, compare directly this figure and this figure. But okay. Anyhow, by taking this ratio, then you may be able to say something about the existence or non-existence of the bound state or quasi-bound state in omega. So this kind of data would be very valuable in the future. And then, of course, the comparison with lattice data in detail would be necessary to make some conclusion. But the message is that having that kind of a source size dependence or peripheral to central ratio. Yeah.
Question.
Yes. Why do? Yeah.
Banga, so maybe you ask your question.
Okay. So that's not the exact cancellation, but
no, wait, there is a question. Excuse me. There is a question. Sorry.
Yeah.
Okay, I don't know. Then I will read the question. Why do Coulomb cancel? So the question is, why do Coulomb cancel in peripheral over central ratio on slide 26?
Yeah. So it's not a strong interaction, therefore it's just a Coulomb interaction. So interaction between the peripheral case, between two particles, and then the central case, they are almost the same. And so it's not the exact cancellation, but you can cancel most of the part by taking the ratio.
Yeah, but I mean, second part of the question is
there's a second part.
Source size, well, because it says that the source
size are different. So
you cannot cancel actually if
the
source.
But at least the Coulomb interaction effect appears at low energy, low momentum, and then this larger the size of the system. In that case, I mean, because you see this K star is less than 0.1 GeV. So, sorry. So I mean, even if the source size is different, at least at low energies, the effect, I mean, it's not the exact cancellation as I said, but the main part of the effect of the Coulomb at low energies roughly cancel. So you can see better resolution for the strong interaction. That is what I think discussed probably Morita and other people. Yes.
Thank you.
Okay. Okay. So I spent too much time on this in omega, and then omega. This is interesting, very interesting, whether there is a bound state, very shallow also or not. And then that could be in the future discussed in the heavy ion collision or PP collision. And then I hope that could be studied in the near future. So I'm just skip this. And then last, maybe, can I have 2 minutes, for example?
Okay.
Yeah. And then the last one is proton phi meson, and then which is a very interesting stuff which it's emerged in recent years. So the question is, what is the force between the neutral particles at long distance, like hydrogen atom interaction? And that is, of course, we know it's van der Waals or Casimir powder if you include the effect of the retardation effect. So it's 1 over R to the 7th potential. In the case of the QCD, it's always 2 pion exchange force that has been discussed by originally by Peshkin, and then the other people, and also further make this discussion more solid. And since if say J-psi interaction, J-psi has a gluonic crowd around, but of course gluon cannot by having the OZI vibrating process, they emit 2 pion and then absorbed into the other J-psi. So J-psi interaction at long distance is mediated actually by the 2 pion. It's interesting, but it's a fact. I mean, at least theoretically, that kind of interaction is mediated by 2 pion, and the same for the nucleon, say omega. Nucleon phi meson, for example, or nucleon omega 2, I think. So we have published a paper very recently, calculate the nucleon phi interaction, and then its whole attraction. I think this is the same for the nucleon J-psi too. And then if you find if you plot the logarithmic of this potential at long distance, what you find is that you automatically obtain 2 pion tail. So although you cannot really see from here, but if you plot the logarithmic of this potential, then you really find, without doing any fitting or anything, you automatically find 2 pion exchange. So at least above 1 Fermi, this is really 2 pion exchange. And actually, this 2 pion exchange is a main source of the large scattering lengths of order 1 Fermi between nucleon and phi meson. And then effective field theory, people have also studied this one. This is phi meson and nucleon 2 pion exchange, and then you have a 2 pion exchange tail at long distance. And before our the theoretical result published, the Alice collaboration have studied this proton phi correlation function, and then they actually find some attraction, although there is no quantitative comparison of the theory and experiment yet. But what they found is that the scattering length is of order 1 Fermi, and that is consistent with what we found. It's order 1 Fermi from the 2 pion exchange. So it's very interesting to generalize this one into the, say, nucleon J-psi interaction, and then whether the scattering length is of order 1 Fermi or of order 0.1 Fermi, which has been discussed by many other models without having 2 pion exchange. So that kind of physics is very interesting to explore. Okay, and then summary. So Lattice QCD, we started to have some realistic hadron-hadron interactions, and then a comparison of the Lattice QCD data with femtoscopy and also hypernuclei. Both are very valuable to make some comparison, and that has been just started. And then it is unlikely to have H-star baryon below lambda. You may have something near n cascade threshold. That is one message. And then omega would be very interesting and should be searched because, I mean, theoretically it is very clean. There is no decay channel other than the weak interaction between this bound state. And then if it exists, this is a second dibaryon other than the deuteron in the SU3 world. It's interesting. And hypernuclear interaction and 3 baryon forces, we are now working on it, and that this is related to the neutron structure. And of course, we are working also on the charm and bottom, like a tetraquark, like TCC or TBB. It's highly interesting to do both experimentally and theoretically. So we are working now on this Fugaku configuration, and so we will produce some result, I think, in a few years in a physical point, so that we don't have to make any extrapolation to the physical point, although we are already very close to the physical point. And then we haven't changed the lattice spacing yet, although it's very small, 0.08 Fermi. So that kind of thing should be also done to make this our prediction more plausible or precise. So stay tuned, and thank you very much.
So thanks a lot, Tetsuo, for this impressive list of new results and promises for the next years. Okay, so I think we can start the question and answer session. So I see Cheminko first. The first to answer. Please go ahead.
Tetsuo.
Hi, how are you?
Chemin here. I'm fine, thank you.
Yeah.
I have a simple questions.
Yes.
You have one slide showing the side, the radius, and the binding energy of a di-omega.
Yes.
Why the arrow bar in the size is so big? You said that it's easier to calculate di-omega interaction than you can interaction. So why the size cannot be determined? What's the reason?
For example, if you look at this omega, although the statistic is better at short distance, but since strange quark does not propagate too much, therefore the error bars at long distance is relatively large. So it's not generally true that it's heavy ones are better. And then long distance is very important for the binding energy and so on and so forth. So that is one of the reasons. I think the main reason of this.
Okay, thank you.
Yeah. Okay, so.
Excuse me, I was muted. Please.
Okay. Yeah. So who is?
The next one is Nushu.
No. Okay.
Yeah. Hi, Tetsuo. Thank you for this very nice talk. I have a question. Just for my understanding, I think it's slide 16. I have a question about
16. Yes.
About the range of the strong interactions, because in your talk, here you mentioned you mostly focus on the scattering length, but on the vertical axis is effective range.
That's right. Yes.
Right. My question is, you see, this is for PP collisions. The size is around the Fermi or so, but the effective range measured on the lattice is 5 Fermi. What does it mean physics-wise? If the overall size is 1 Fermi, how do we, in the measurement, how do we see the 5 Fermi, the effective range?
I mean, effective range, effective range is an effective range between the lambda interaction. And effective range, I mean, typically it is the size of the potential, but it can vary. It can be larger or smaller, I mean, depending on the interaction. So effective range is just a parameterization of this, how the phase shift changes, the bend. If you have only attraction, you just go up, and then how it bends, and that is parameterized by the effective range, right? And then, so I don't have much intuition, although if it is infinite or very large, say 10 Fermi, 20 Fermi, then it's a little bit weird, but the 5 Fermi is, I think it's not that strange number. That is fine.
In case of at least data for proton 5 method, I think that's page 31.
Page 31.
Yeah, it's also very large, around 10 Fermi.
Okay. That's right.
I just conceptually I do not know how.
Okay. Yeah. I actually, honestly speaking, I don't know too. Effective range, I don't have much in.
You see, it's about an 8 Fermi.
It's yeah. So this is the fitting using LL formula, but in our lattice, in our lattice data, we have calculated the effective range. I don't remember the number. If Yan Liu is in the audience, you can just say what is the number for the effective range for this?
Yeah, excuse me, it's around 2 Fermi.
2 Fermi. So in the case of the so in this case 2 Fermi.
Yeah, but if I can chime in, I mean, first of all, so it's not that the distances in PP collision are 1 Fermi. I mean, is the Gaussian width, which is 1 Fermi. Most probable distances are around 2 point something Fermi, and you have a tail You have a distribution up to 6 Fermi and so, and also the effective range. I mean, okay, if you look at the analytical formula, the Nitsky-Luboschi formula, it is basically, I mean, is the second order of the expansion of the scattering parameter. So basically, it is, I mean, it's correlated with the derivative, if you want, with the shape of the correlation function. So it is, but still, the fact that it is for lambda-lambda, I think the effective range also extracted from. So if you go to the lambda-lambda figure, so also the effective range extracted from hypernuclei data, right? That would be this data point in yellow somewhere. Oh, yeah, so this is this yellow star, right? This is H, K, M, J are the hypernuclei, double lambda hypernuclei, I think.
Okay.
So they also get a similar value. For proton phi, the truth is that this number that it's published, it does not distinguish between spin state. So the phi proton has 2 spins, so 3½ 1/2. So in this first work did not distinguish. So it's an average number. Now, in order to see in detail the detail of the interaction, one should try to study it more. So I would not take this number seriously.
I see. Can I just follow up, because this is a question to theory. Now, my question on your calculation on the lattice.
I've done that before on the TFG library, and I think it might be good.
Wuchang, are you talking? Wuchang.
I'm sorry.
Oh, yes. You. Okay, so on the calculation, does this parameters D0, F0 depend on the overall size? When you do calculation, does it depend on the size you assume in the calculation?
Size means the lattice box, right?
Right. Yes.
Yeah. I mean, our potential is the size is something like 2 Fermi, which is much smaller than the 8 Fermi box, or even the 4 Fermi. So I mean, in our calculation, we haven't shown explicitly we haven't done any calculation for the different lattice sizes. But before before K configuration, we have done the simulation with the different lattice sizes, and then as far as the lattice box is enough large compared to the potential range, the result doesn't change. So,
okay, thank you.
Okay, so the next question is Wuchang.
Yeah, I have a question about the size, because there is uncertainty in terms of the size in heavy ion collisions. Yes. And it's not just the Gaussian, the collision system is so dynamic.
Yeah, right, yes.
So, and I don't have a direct feeling how much uncertainty that has on your interaction. You know, you can compare your calculation with data and to extract information about information.
Yes.
What would be the uncertainty on your interaction parameters due to the dynamics of heavy ion collisions?
Yeah, that has not been. Precisely studied, I think, but at least in one of the paper by Morita, they have calculation for the P omega and omega omega. They have calculation with the static Gaussian source, and then also they use the RIKEN type, the expanding source. And then qualitative behavior doesn't change, but of course the curve itself quantitatively different. So we really have to do this kind of comparison in detail. Yeah, at least in the case of the heavy ion AA collisions. And certainly, I think it's not just a static Gaussian. Maybe it's better to use expanding, and that kind of study has been already started. So, yeah, we have to make it more precise in the future.
Okay, thank you.
Yeah.
Are there any other questions or comments? Okay, I have a question about the lambda-lambda discussion, because somehow, so you said that the possibility of having now a lambda-lambda bound state in H baryon. I mean, it's not completely excluded, but very unlikely. But now, what I did not understand is what can we do to eventually close the case, demonstrate that lambda-lambda cannot be bound to an H baryon. Which kind of measurement do you need?
Experimentally.
Yes.
I'm not sure. Other than this correlation measurement.
No, but also for the, can you go back? I mean, you have this involved couple channel system in which, okay, we can improve.
This one?
So
this kind of thing, or?
Yeah, so now we can improve on the precision of the measurement of proton psi minus and lambda-lambda, right?
Yes.
But if these measurements now would be extremely precise, imagine you at percent. Could we then draw a conclusion or not?
I think so, because this lambda-lambda, this kind of data, if it becomes very precise, then it should be able to tell us about whether there's a the bound state or not. For example, by changing the source, PP, comparing, this is PP, but you can do PA or AA, and then you can see the
and
behavior.
then if this is steady, then okay, this is still the way to go. Okay.
Right, I guess, yeah.
Okay, thank you. Okay, we have another question by Nu. I don't know if for fusion was the old one, but okay, let's have the question by Nu first, please.
At the very beginning, you tried in your introduction slide, you say study in collisions, the hypernuclei, then we can connect to neutron star. We know neutron star, there's one condition I think is extremely different, that is isospin, tremendously different.
Yes.
But do we really have a connection, even theoretically?
I think,
between hypernuclei and neutron star.
But that isospin is isospin asymmetry between neutron and proton, right? And then the isospin symmetry which we assumed is just a UD Koch mass difference. So that is relatively a tiny effect. And then rather, we need to discuss, say, how the lambda neutron interaction, or what is the lambda neutron three-body interaction. That is very important. So that kind of three-body force is really relevant to the hypernuclei, and that can be done in principle, and then we are hoping to do it in the future. But three-body means you have to put 3 nucleons, and then it's not trivial. It's not enough to just put 3 lambda and neutron in the box. You have to subtract out the lambda n interaction and n interaction to really, get the genuine three-body force. So you have some subtraction involved, and then there will be error accumulated and so on and so forth. So as far as formalism is concerned, you can do it, but technically, numerically, it's rather challenging task. Not impossible.
But in case of neutron star, the density is also very high. Are we still using the language of nucleon degrees of freedom?
Right.
We have to use the quark level. So
exactly. Yes. So eventually, that kind of our nucleon degrees, description will break down. So we cannot use this kind of 2-body, 3-body stuff for forever. Maybe above 2 or 3 times nuclear matter density. Eventually, some sort of the percolation coming in. So it's another story, which we cannot do anything using this approach. So we have to really develop new lattice QCD simulation for the finite chemical potential, and that has been sought for many years, but nobody has still any progress, real progress yet. So maybe some quantum computation of this lattice QCD in completely different way may solve the problem in the future. But,
when we do correlations, for example, those are basically after freeze out. The density particles is relatively low, very low comparing to neutron star case.
That's right.
Maybe the real question is what we learn here. much
For
can propagate for studying neutron star, the structure.
So the answer is that we have to go step by step, by starting from 2 nucleon and 3 nucleon, and hopefully in the future 4 nucleon, something like this. I cannot imagine the other other direction.
Thank you.
I have also a question about these 3-body calculations for lambda NN or lambda proton. So what is the horizon for the availability of calculation on Fugaku for these systems? So when do you
mean
think?
when? That's difficult.
When?
That's very difficult. I mean, at least for the 3 nucleon case, in the simple calculation in the relatively small box, and then the large pion mass has been done, and we have one paper published by Doi-san. But realistic calculation, at least for the relatively heavy quark masses, probably we may be able to do something. So we may be able to do some heavy pion mass calculation, and then get some qualitative behavior. That I don't know, in a few years or something. But realistic one, I have no idea at the moment. Formalism is there, but
I was wondering because there will be measurement of triplets. Triplets, yes, next year. And but
not that soon, right?
Rather soon, yes. So any other questions or comment? Okay, so I don't see any reason end. So I don't know if I have to give back the word to the main organizer, or I can just okay, maybe since I don't see anybody so wanting the word, then I would like to thank you, Tetsuo, for the nice talk, and also all those who participate with the questions and in the discussion. And I guess I wish you good rest of the day or of the night, depending where you are. So see you soon. Bye-bye.
Thank you very much. Bye-bye.
Thank you.
Bye.
Thank you all. Okay.
Bye. If you know when you come to the lab, please let me know. Normally I stay at home, so I will come to see you. Did you say you will come to, because normally I'm at home. If you tell me when, I can.
Either Friday or Monday, I may come, but I'll let you know. Yes, by email.
Yes. Thank you.
Thank
you for the nice talk.
Thank you.
Okay. Thank you so much. Okay.
Thank you very much.
Okay. Bye.
So bye-bye.
Bye.
Bye.